This video deals with universal gravitation, and this is the first part which contains basic gravitation, its concept, definition, gravitational field, and few related questions that will cover up the basic theory that we will be discussing. Now, universal gravitation means it was first of all given by Newton. So that is Newton's universal law of gravitation, we can say it. So Newton's universal law of gravitation states that any two particles in this universe, this is particle of mass m1, this is particle of mass m2. If these two particles are at a distance, let us say small r between them, then they exert force on one another. That is, one particle attracts the other particle. Similarly, the other particle also attracts the first particle with equal and opposite force. So let us denote this force by F. So this force is equal to some constant into product of the masses divided by square of the distance between them. This is the beginning of the basic concept of Newton's universal law of gravitation, where m1, m2 are the masses of the particles and small r is the distance between them. So basically, this is defined for point masses. It is defined for point masses, where the masses will not have any dimensions. It is basically for point masses. Now, later on it is found out that it has been found to be true for spherical bodies also. It is found to be true for spherical objects also. Here, the quantity, that capital G that we have denoted, this capital G is called universal gravitational constant, and its value has been calculated as 6.67 into 10 to the power minus 11 Newton meter square per kg square. So now this capital G, which is used everywhere the same value, it does not depend from time to time or place to place, it doesn't vary. That is why it is called universal gravitational constant. So what I said, that universal gravitation starts with the concept that has been defined as the force between two point masses as G m1 m2 by r square, where small r is the distance between the two particles. So we can find out the force as per the calculation between any two particles in this universe. Let's see that few other aspects. Let us define gravitational field intensity. Gravitational field intensity. Due to a mass, let us say this is a mass capital M. Now this mass will definitely ready to exert force on other masses that are placed in its surrounding. So let us say at a distance small r, we are placing another mass small m. So that mass small m will be experiencing force. So that force, how much force it will be experiencing, that force will be equal to the magnitude of the force, that will be equal to G into first mass into second mass divided by r square. Is it not? So this particular mass will be experiencing force of this much. Now gravitational field intensity is defined as the force acting per unit mass placed at a particular point. So let's say P is the point. So therefore we can say at the point P, the Gravitational field intensity. The gravitational field intensity, if I denote it by capital E, it is a vector quantity, is defined as force acting per unit mass, that is F by m. So if I divide by this small m, then what will I get? See, this small m I am going to divide this result with. So what will I get? I will be getting the magnitude as gm by r square. So if I take only the magnitude, the gravitational field intensity due to the mass capital M at that point, it comes out to be G into M divided by R square. So what is gravitational field intensity? First of all, it is produced by a mass. This influence produced by a mass is the force acting per unit mass placed at any other point. Means first of all there should be a mass who will produce this effect, and secondly there should be a mass who will experience this effect. That is, experiencing is only on unit mass. So just check it. What is the unit of gravitational field intensity? The unit will be equal to force acting per unit mass, that is Newton per kg. Newton per kg will be the unit of gravitational field intensity. What can be the dimensions? The dimensions will be force divided by mass. Now I hope you are aware of that force is equal to mlt to the power minus 2 divided by the mass, that is m. So finally we have L t to the power minus 2 is the dimension of gravitational field intensity. Now let us see again that particular force which we defined as force is equal to Gm1 m2 divided by r square or x square. So what I told, that this will be defined for point masses, and also it is found to be true between spheres or particles. Point masses means particles. That is, if this is one sphere and this is another sphere, and center to center distance between the two spheres is smaller, this mass is m1, this mass is m2, so one will attract the other, and force of attraction can be written as g m1 m2 divided by r square. Please remember that if this is a sphere and instead of this is a particle, and the center of the sphere to the particle, this distance is r, the masses are m1 and m2, then we can have force is equal to gm1 m2 divided by r square. Plus, now please note that if it is not a sphere, or if it is neither a particle also, rather this is an irregular shaped object, this is also an irregular shaped object, and this is the center of mass, this is the center of mass, and small r is the distance between their center of masses, where the masses are m1 and m2, then we cannot write gm1 m2 divided by r square, where small r is the distance between the center of masses. That is, please remember, this is not valid, this is not defined if r is the distance between their center of masses of irregularly shaped objects. That means this is only defined for point masses, and it is defined for, I said, spheres, or a sphere and a particle, that is a sphere and a point mass. Therefore, if for irregular shaped object, if I take it as irregular shaped object, then for irregular shaped objects, this force cannot be written as gm1 m2 by r square. So just by saying that it is the distance between the center of mass, we directly cannot apply gm1 m2 by r square formula. It is only valid for Now let us take an example where we will be learning how to utilize the Newton's universal law of gravitation formula. Let's take an example. Suppose this is a rod. It's a uniform rod whose mass is capital M. So rod mass is m, length is L, and this is a particle whose mass is m, and the particle is at a distance small r from the nearest end of this rod. So there will be mutual gravitational force of attraction between the rod and the particle, because every particle, every object in this universe attracts every other particle. That is what we basically know from the law of gravitation. So what is the question? Question is, find the force of gravitational attraction between the rod and the particle. Find the force of gravitational attraction between the rod and the particle. So what I have advised, you cannot directly take the center of the rod, which is the center of the mass, to this particle as the distance. So what I will do is, the solution part should be like this. Let us divide this rod into various small elements. Let us divide the rod into several elements of infinitesimally small lengths. That is, the lengths of each small element will be extremely small. And let us now consider one such elements. So now again let's check. This is the rod and this was the particle. So from the particle at a distance x, I am taking a small element, very small element, whose length is dx. It is so small that it can be regarded as if it is a particle. Now, what is the length of the element that we have considered? Length of the element can be written as, see, the total mass of the rod is m. If I divide the total mass by total length, what will I get? Mass per unit length. This multiplied by dx, which is the length of the element, it will be the length of the element. And now I have ready-made multiplied by the length of the element with the dx. That means I have got the mass of the element. So let us directly take the mass of the element as m by L dx, because the length of the element is dx. Now this element is just a small particle. This small particle and the other particle which is having mass m, they will definitely have a force of attraction. Is it not? So therefore, we can say elementary force of attraction, elementary force of attraction between the element and the particle which is given will be how much? It should be equal to g into mass of the element, which is m by L dx, into mass of the particle divided by the square of the distance between them. Now, if such kind of many elements can be taken, therefore the total force of attraction, that is, I mean to say the gravitational attraction, total force of attraction between the particle whose mass is m and the given uniform rod whose mass is capital M will be how much? A suitable integration of such forces, is it not? Let us suitably integrate it. So F will be equal to integration of g m by L dx into x divided by x square, where x varies from r to r plus L. Just have a look again that what I have taken as x varies from which place. See, this is the nearest distance, no? This is the nearest distance r, and the farthest distance up to the other end of the rod is r plus L. Is it not? Therefore, I have varied x from r to r plus L. Therefore, what we have further, let's solve now. Is it not? Let us have a solving part. G capital M by L. This is what? This is taken out. Is it not? This is taken out. Now, one small error I have mentioned just here, x, it won't be x, no, it will be m. So one small m also comes out. And now we have 1 by x square dx, where x varies from r to r plus L. Please check it. Then f becomes equal to gmm divided by L. Now integration of 1 by x square is minus 1 by x, varies from r to r plus L. I am putting the respective lower and the upper limits. First I am putting the upper limit. So minus 1 by r plus L minus lower limit I am putting in place of x. It is minus 1 by r. So now what I am getting is this force finally comes out to be GMM divided by L. Now within the bracket it is 1 by R minus 1 by R plus L. A little more within the bracket it can be simplified. It is equal to R plus L minus R divided by R times R plus L. So what we get as that F is equal to GMM divided by L, and in the numerator it will be L divided by R plus L. So L gets cancelled. We have GMM divided by R times R plus L will be the force of attraction between the rod and the particle. Just have a quick review of this particular question. You will be able to have an understanding that the force of attraction between the particle and the rod comes out to be this much. Now let's see a few other examples. Suppose we have three particles which are exactly placed in such a way that if I join them, it forms an equilateral triangle. Let's take the mass of the particle is same as m, and they form equilateral triangle. Now the side of the equilateral triangle, let us say each side is equal to a. Each side is equal to A. Now, under this case, there will be gravitational field intensity at different points that we can check. Have a quick look at what is gravitational field intensity. Gravitational field intensity is basically, it is at a point. This is force acting per unit mass. Force acting per unit mass, whatever mass we keep it. Now let's see what is force acting per unit mass. It will be equal to gm by x square, where m is the source mass which has produced this influence. Please remember, this m is the source mass that produces the field. And what is the direction of gravitational field? The direction of gravitational field is, at any point, the direction of gravitational field is towards the mass, or towards this point mass which has produced it. which has produced it. Now let us try to recognize from this example that how do you calculate, how do we find out the gravitational field intensity at different points. Again, I am trying to draw without disturbing the main figure. I am trying to draw the triangle again, and at the vertices of this equilateral triangle there are point masses. Now check. If this is a point mass, this is a point mass. For the time being, let us forget that there is the third point mass. I am taking the center of this side. At the center of this side, what will happen? The first point mass will exert a gravitational field intensity towards it. This will be E, and this other point mass will exert a gravitational field towards it. Do you feel that the gravitational field intensity will be same? Yes, they will be same because this mass is also m, this other mass is also m, and every mass exerts a gravitational field intensity which is towards this mass. So therefore they will counterbalance one another. Is it not? This field will be zero. Then at that particular point, who will be producing the gravitational field intensity? It will be produced only by the third mass. Is it not? This third mass will produce a gravitational field intensity at this particular direction, which is equal to, let us say, E or E dash, whatever. So what is E dash then? Then we can find at this particular point the net gravitational field will be equal to produced by whom? Produced by this particular mass, that is m, which is equal to g into that mass who has produced it divided by the distance square. How do you find the distance? This distance I am talking about, this distance. Now what are the sides? This is side A. This side is a by 2. So I hope you will agree if I write this side is equal to root 3a by 2. So therefore the distance is equal to root 3a by 2 whole square. So finally what should I write? I can write 4gm divided by 3a square, and direction I have specified. This is the direction of the gravitational field intensity at that point. And whatever is true at this point will be same true at the respective centers of the other sides also. Is it not? They will be. So at different points we can find out like this the gravitational field intensity. And now let us try to find out the gravitational field intensity at any of the vortex. Please remember that a mass cannot produce the gravitational field intensity, I am denoting by E, at the location where it is itself placed, where it is itself placed. That is, a mass wherever it is, it cannot produce a gravitational field intensity at its own location. It will be producing at other location. Now let me again draw the equilateral triangle. This is equilateral triangle I am drawing. At the three vertices, the three masses are present. Roughly, I am drawing. Now this is the point where I am going to find out the gravitational field intensity due to the other two masses. These masses are m and m. So what are the gravitational field intensity produced by this? Let us try to find out. Let's see that how much the gravitational field intensity it produces. Here, this will produce a gravitational field intensity which is equal to capital E. Let us say this is equal to capital E. So this is capital E. I am taking this. And the other mass will also produce a gravitational field intensity which is equal to capital E. Is it not? This is gravitational field intensity which is equal to capital E. Now the third mass which is already placed at that vertex where we are finding out, this third mass cannot produce a gravitational field intensity at its own location. So what is the magnitude of gravitational field intensity? Now let's check. Be produced either due to the first or the second, it is equal to G into M divided by what is the distance? Distance is A only, the side of each of these edges of the triangle, that is Gm by A square for both. Now see, both of them are vectors. And what is the angle between these two vectors? The angle between these two vectors is 60°. So by law of parallelogram of vectors, we can say the E net value will be equal to, just in which direction the net value E will be there. E will be there, the net value, it is nothing, exactly it will be directed downward, that is along the angle bisector. You know that if two vectors are same, then the resultant is along the angle bisector. And what will be the resultant? Will be root over the first square plus the second square plus 2 times first into second into cos of the angle between them. Let us take out E square common, so it will be E root over 1 plus 1 2 plus 2 cos square theta, sorry, cos theta only, so half. So this is root 3 times E, and E is equal to Gm by A square. This is the gravitational field intensity along which direction? Along this particular direction, which is the right bisector of the opposite side. So the direction, we can say it is directed along the normal bisector of opposite edge, normal bisector of the opposite edge. Like that you can find out the resultant gravitational field intensity. Again, let us take up the same example where we have taken the three particles. They are placed at the vertices of an equilateral triangle. I am putting stress on these particles because you can easily apply basic geometry for other symmetrical once you can understand this basic logic. Now let me take a point which is at the centroid of this triangle. Exactly at the centroid, all the three will be producing their own influence. This first particle, it will be developing its own gravitational field E. And you know that the centroid is at the same distance from the three vertices as it is equilateral triangle. This will be also producing E. And the third mass, that will be also producing the same gravitational field E. Now, I hope that you are aware of what is the angle between these. The angle between these will be equal to 120°. The angle between these will be 120°. I hope you are aware of this, that the angle between them is 120°. Is it not? So, we can have this 120 here also, 120 here also, 120. So, what will happen? As the three equal vectors, that is gravitational field intensity, have 120° angle between them, hence the resultant is 0, because any two of them will be producing their resultant exactly opposite to that of the third one. If this is E, this is E, and the third one is also E, you know that when that angle, when the two vectors are equal, then the resultant will be exactly along the angle bisector, is it not? So this resultant will be exactly along the angle bisector. And how much is this resultant? This resultant will be equal to root over E square plus E square plus 2 times E into cos of 120°. So this becomes how much? Root over 2E square plus 2E square into cos 120° is minus half. So ultimately we are having how much? Root over 2e square minus e square, which is equal to e. Now this e, which is exactly along the angle bisector, will be counterbalancing this particular e. That is why we have taken the resultant is 0. That is, at the point of symmetry we understand that the resultant is 0. The resultant gravitational field E net is zero vector or a null vector at the point of symmetry, at the point of symmetry of any geometrical arrangement, of any geometrical arrangement. In support of this, let us take another example where you will be able to understand the concept of point of symmetry. Let's say that I am taking four identical masses, each mass small m, and they are placed in such a way that they, if I join, they form a square. Each side, let us take m masses, and each side is a. Now if I take this particular point, which is the center of symmetry of this square, then do you feel that the gravitational field intensity will be same? This E has to be counterbalanced by this E produced by these two diametrically opposite masses. And this E will be compensated by this particular E due to the diametrically opposite masses. So what can I conclude? That at the center of symmetry of a square arrangement, at the center of symmetry of the square arrangement, the gravitational field intensity net value will be 0. Let us try to extend this. I am taking a pentagon, a five-sided figure. Let's say that 5 point masses of values m each are going to be placed at the vertices of a regular pentagon, as I have tried to show in this figure. Now I am leaving in your discretion that you try to reason out with the help of geometry, that if I take the point of symmetry where every vertex will be equidistant from the point of symmetry, we have five vectors, all are having magnitude E. You investigate and try to convince yourself that the gravitational field intensity will be 0 at the point of symmetry. That is, net gravitational field intensity will be 0 at the point of symmetry. I am further extending it for hexagon, and then you see what happens. That let us say that I am taking a hexagon where the 6 particles, they are placed at the vertices of this regular hexagon. Each of mass m. Then if I take the point of symmetry of this regular hexagon where every particle will generate its influence, that is gravitational field intensity, I hope you can very easily investigate that the net gravitational field intensity will be 0 at the point of symmetry of this hexagonal arrangement. All are capital E. So net value of E, that is also 0 at the point of symmetry. Like this, if you extend it for any symmetrical system, you will find that the gravitational field intensity is 0 at the point of symmetry. Now, if they are not identical, then if masses are different or the distances are different, then we need to find out. Just for example, if I take that again, I revert back to a triangle. Either the sides of the triangle are different, or suppose sides are same, the masses are different. Anything you can take. As per the calculation, we need to accept the result. Let's say this is equal to m, this is equal to 2m, and this is equal to 3m. And if I try to find out that what is the net gravitational field intensity at this point of symmetry, then we need to find out E1, we need to find out E2, and we need to find out E3. Angle between them is 120 degree. So what is E1? First of all, you need to know the distance. The distance between each point and the center will be how much? The median is equal to root 3a by 2. So the distance between centroid and vertex will be how much? Median divides it in the ratio 2 is to 3. So 2 is to 1. So 2 by 3 times root 3a by 2. So it becomes a by root 3. So the distance is a by root 3. Therefore, each of them we will be in a position to find out. E1 you can find out as g into 2m divided by a by root 3 square. Similarly, E2 and similarly E3. I hope you can find out the resultant E1, E2, E3 and you calculate. This is just as an exercise for you people. Calculate the resultant gravitational field intensity at the centroid, keeping in mind the angles as well. Now, after having a little introduction about the gravitational field and the force, let's take other example to understand it better. So, to find the gravitational field intensity due to a semi-circular wire frame at its center, of course. So let us say there is a semi-circular wire frame having some mass will be given, some radius is, it is very thin, the thickness is negligible. The mass is equal to capital M and the radius is understood to be R. At this particular point, we need to find out the gravitational field intensity. You can join it with the help of dotted line for your reference. What I will do is, I will divide this entire semicircular wireframe into small elements. And one such element I am considering like this. So this element is subtending, it is so small that it is subtending a very small angle at the respective center. Let's say the angle is d theta and it is taken at an angle theta from this side and it subtends an angle d theta. So what I am taking that, let us take a very small element subtending an angle d theta at the center, and I have taken it at an angular position theta as I have shown in the figure. So exactly at this particular point O, as there is no space, I am again trying to show on that line I have taken that point O, is it not? And the element I have taken here. This element is here which subtends an angle d theta. I have already shown that d theta. So the element is so small that it is regarded as if it's a small particle. So this particle will be generating gravitational field along this direction d to the particle. Towards this particle it will be subtending. Now what is the mass of this particle? Mass of the particle, if you for the time being denote it by dm, this is the dm is the mass of the particle. See, the total mass is capital M. If I divide the total mass with the total length of the semicircular wire frame, the total length is half of the circumference, pi r. So what I get? Mass per unit length multiplied by the length of the element, it is r d theta. So this is mass of the particle. So if this is the mass of the particle, how much gravitational field intensity? Only due to the element, elemental particle. It is elemental particle. How much the gravitational field intensity will be generated? That dE will be equal to G into mass of the particle. Mass of the particle is m by pi d theta divided by r square, because you are able to understand that this 2r gets cancelled. That is why it is m by pi d theta. So we have finally gm divided by pi r square d theta. What is this? This is the elementary gravitational field due to the element. Now this field will be having two components. This field will be having two components. What are the components? Let's check. As that is theta, so this will be equal to dE sine theta, and the other component will be equal to dE cos theta. Can you understand that this dE cos theta is going to be cancelled by another dE cos theta of a symmetrically placed element which I could have taken at this particular location? That will be also generating its dE cos theta. So what I can understand is the element dE cos theta will get cancelled by another symmetrically placed element. So therefore, effectively, if I calculate the gravitational field intensity, then gravitational field intensity will be the summation or the suitable integration of all the sine theta components. The sine theta, this dE sine theta component of all the elements, they will be getting added up, and all the dE cos theta components, they will get cancelled. So now what is dE? dE is equal to Gm by pi r square d theta, and this sine theta will be there. So sine theta d theta is suitable integration. Now let's check. I have to consider the elements from one end to the other end. Therefore, theta starts from 0 and it goes up to 180 degree, that is pi. I have to add the sine theta components produced by all the elements, and d cos theta components will get cancelled out. So now therefore, gm divided by pi r square, and the integration of sine theta is minus cos theta. Therefore, it is to be put the limits, that is upper limit and the lower limit. So we have g m divided by pi r square minus cos pi minus of minus cos 0. So what I get is as gm by pi r square minus, and cos pi is minus 1 and cos 0 is 1. So finally we get 2. So this is equal to 2gm divided by pi r square. This is the gravitational field intensity, and the direction of gravitational field intensity will be always along the axis of symmetry. This direction, this is the axis of symmetry. Along this is the axis of symmetry. So this is axis of symmetry. So along the axis of symmetry, the net field is directed. So we can mention it, it is directed along the axis of symmetry. So that is the gravitational field intensity due to this semicircular wireframe whose mass is m and radius is r. In the other example, we will find out the gravitational field intensity due to a complete ring on its axis. So, gravitational field intensity, in short I am writing, due to a ring we are taking, due to a ring, uniform ring, whose mass I am taking m and radius r along its axis. Just observe that this is a ring, a uniform ring, and along the axis we need to find out at a certain point I am taking here, which is at a distance x from the center. The mass is m, radius is r, and it is at the x from the center. I take a very small element anywhere. So as it is on the perpendicular bisector, that is, this particular dotted line is perpendicular to the plane of the ring. Therefore, it can be easily understood that any point of the ring will be equidistant from the point on the axis that I have taken. So now, if I join it at that particular point, the elementary gravitational field created by that element will be equal to this dE or delta E, whatever you call it, this dE. And this element is equal to delta M, a very, very small element I have taken. Now, what will be dE? This dE is nothing but G into that small element who have contributed it divided by distance square. What distance should I write? The distance is root over x square plus r square, because radius is nothing but r they have given in the condition. So we can have Gm divided by the distance square, basically it will be r square plus x square. This is dE. Now what about angles? If this angle I am taking as theta, then I can write that dE cos theta will be along the axis and dE sin theta is perpendicular to the axis. Now you will be very easily able to understand that this dE sin theta will get nullified by another dE sin theta, which might be produced by another symmetrically placed element that I can find out here. So it is easy to understand that the component dE sin theta will get nullified by two symmetrically placed elements. Two symmetrically placed elements. Therefore, we need not think about dE sin theta component. We will be only thinking about dE cos theta component. So therefore, what will be the net value of gravitational field intensity? Of course, the net value will be along the axis towards the center. So this will be summation of all such dE cos theta components. Now, what is dE? dE, we were observing that dE is equal to G delta M divided by x square plus r square. Let's put that value here and try to observe that what we can say, that is here G delta M divided by x square plus r square. And what is cos theta from the triangle? Cos theta is x by root over x square plus r square. Its summation. Now for a particular point x is fixed. From here we can have G is constant divided by x square plus r square to the power 3 by 2. X is there and summation of all the delta m, and summation of all the delta m will give us the total mass of the ring. Therefore we have gmx divided by x square plus r square to the power 3 by 2. This is the gravitational field intensity at a distance x from the center and on the axis gmx by x square plus r square. A few more aspects are to be ascertained by looking at this. See, at x equal to 0, if I put directly x equal to 0, so gravitational field intensity is 0 at the center. And if I put at x tends to infinity, infinity means very far away. So if I put infinity, then gravitational field intensity will be its limiting value as x tends to infinity, the value of gmx divided by x square plus r square to the power 3 by 2. Here it also tends to 0, because if you divide by x, ultimately, and then in x you merge inside this denominator, then and find out the limit, that is 0. So gravitational field intensity at very far away along the axis is also 0, and at the center is also 0. So very easily we can conclude that gravitational field intensity is starting from 0, and then at very far away place also it will be 0. So let us try to study first of all roughly the variation of gravitational field intensity versus the distance from the center along the axis. This is gravitational field intensity and this is x. So at x equal to 0, the gravitational field intensity is 0. Only magnitude I am denoting here. Therefore, it starts from 0 and ends at 0. So definitely we can say that somewhere in between the gravitational field intensity might have become maximum. It increases, becomes maximum of course somewhere, and again it begins to decrease and finally it becomes 0. The same thing takes the nature at the other side also. The gravitational field intensity increases and then again it deteriorates to become 0. That is, we need to find out that what is this particular point at which the gravitational field intensity is maximum. Both the distances are from the center on both the sides. Therefore, any one side if we can find out, then it will help us to locate the particular point at which the gravitational field intensity is maximum. So, for gravitational field intensity to be maximum, we have to take dE by dx is equal to 0. And after putting dE by dx equal to 0, we will be in a position to find out the gravitational field intensity, where it will be maximum, and then what will be the maximum value of the gravitational field intensity. Now we have the gravitational field intensity as we just now observed as is equal to E is equal to G mx by x square plus r square to the power 3 by 2, where x is the distance from the center, where x is the distance from the center. Now we were trying to find out where E will be maximum. Let us differentiate. D by dx is equal to Gm. Now in the denominator we square it. So x square plus r square to the power 3. Now in the numerator we just leave x square plus r square to the power 3 by 2. We differentiate x, which is 1, minus. Now we leave x and we differentiate the denominator. It is 3 by 2 x square plus r square to the power 3 by 2 minus 1, and then the differentiation of the inside, which is 2x, and this is equal to 0 that we are going to put. So this implies this gm goes, denominator goes, we have x square plus r square to the power 3 by 2 minus, and then we have 3x square, and then x square plus r square to the power half is equal to 0. Here, cancelling x square plus r square to the power half from both sides, we have to ensure, because x square plus r square is never equal to 0. If a quantity is not 0, then only it can be cancelled from both sides. So we have further that x square plus r square out of 3 by 2 half gone, minus 3x square is equal to 0. So we have r square minus 2x square is equal to 0, that is x equal to r by root 2. So let us try to remember that we can take it to be plus or minus r by root 2 from the center at a distance r by root 2. The gravitational field intensity should be maximum. The gravitational field intensity is maximum at a distance r by root 2 on both the sides. And what is the value of maximum gravitational field intensity? The value of maximum gravitational field intensity can be found out by putting r by root 2 in place of x. That is g m x divided by r square plus x square means r square by 2 to the power 3 by 2. Gm r divided by root 2, and we have 3r square by 2 to the power 3 by 2. So this becomes gmr divided by root 2, and we have r to the power 3 and 3 by 2 to the power 3 by 2, and you can adjust the value if you wish, and then finalize that this will be E maximum, it is equal to Gm divided by r square, and this you take it as root 2, and this you take 2 by 3 to the power 3 by 2. This is the maximum gravitational field. And the rough drawing that time we were trying to draw, a roughly drawn graph should look like this, that gravitational field intensity, it increases, becomes maximum, again start deteriorating, and on the other side also it increases and then start deteriorating and becomes zero at a very large distance. And this particular value where it becomes maximum, it is equal to r by root 2. This is x distance from the center, and this is E, and this particular value, this side also this particular value, this is E maximum, which has been found out by putting r by root 2. So this is also minus r by root 2 on the other side. So this is the variation of gravitational field intensity due to uniform ring on its axis. So on the axial line, the variation of gravitational field intensity can be studied as this. And the expression E is equal to gmx divided by r square plus x square to the power 3 by 2. The graph belongs to this particular mathematical expression. We will continue this in our next classes. You keep watching after this.